Hi and welcome to this Leaving Cert Higher Level video. In this video we're going to be focusing on coordinate geometry of the circle. And within the coordinate geometry of the circle course, this video is going to deal with two circles. So we're going to talk about common tangents and common chords. So we're going to look at questions where the circles touch or they overlap. So we're going to see examples of how to find the equation of a common chord or a common tangent of two circles, to find a point of intersection between two circles, and we're also going to investigate if circles touch internally or externally. So before we start, I just want to bring your attention to page 18 and page 19 in your log tables. Although the page 18 and the top of page 19 are all line formula, these formula come up quite a lot when we're dealing with circle questions. And this is because a lot of what we do with this circle is linked into what we already know about the line. Page 19 at the bottom half has the circle formulas. So there are two sets of circle formulas. Here we have given center hk and radius, or the equation of the circle is x minus h squared plus y minus k squared equals r squared. So I'll just highlight where I'm reading. So we're looking at this one here. So that equation formula is the one we tend to use when we're building the equation. And I say tend to because it's not 100% rule, but we usually use that one if we're building the equation. It does depend on what information we have. Then the next one says given the equation. So these kind of three pieces underneath, or two if you're not using the tangent formula, tend to be the ones that we use when we have the equation of the circle and we want to work with it to pull out the center, to pull out the radius. So those are covered, those kind of examples are covered in another video. I'll link the other two circle videos in the description if you want to look back on how to build the equation of the circle and how to work with it and how to work with the tangents as well. So look at this circle here. We have a lot going on. We have some things that we know, and some things that you should know are the diameter, which is a line that goes from one end of the circle to the other, but it goes through the center. We also have the radius, which is half the diameter, or it goes from the center of the circle out to the edge of the circle. One of the ones we've talked about in the last few days has been a chord. So a chord is a line that cuts the circle. And remember that the diameter is actually a special chord that goes through the center. We then have an arc, and this is something you probably came across when you were doing your constructions at junior cert. So arc is like a part of the outside of the circle, so it's part of the circumference. We then have tangent here. So our tangent AB, it touches the circle only once. And the last thing that's in this diagram is segment, which is up here, which is a piece of the circle. And it's a very specific piece of the circle. Look at the way that it's cut. We also have a sector. So a sector of the circle, which we'll look at in a lot more detail when we're doing our trigonometry. And that will be the sector. So our sector would look like a slice of pizza. The segment is what is cut off using a chord. So now we're going to go through some of the circle theorems. You don't need to write these out if you're watching this instead of being in class. There is actually a little printout that's about half an A4 page for you to stick in. So at this point you should have had your keywords, you should have had that circle diagram that we had on the last slide, and then this circle theorem sheet will be stuck in. So if you're taking down notes, leave a space. So there are two main theorems in a corollary. So the first theorem is theorem 20, which is about tangents, and it says each tangent is perpendicular to the radius that goes to the point of contact. So that's saying a tangent and a radius are perpendicular when at the same point, and you can clearly see it over here on the right. It then has the second part of the theorem, which states if P lies on the circle S, and the line L is perpendicular to the radius at P, then L must be a tangent. Okay, so we can work this both ways. If I know it's a tangent, I know it's perpendicular. If I know it's perpendicular and touches the circle, it must be a tangent. So the corollary of that theorem, theorem 20, is if two circles intersect at one point only, then the two centers and the point of contact are collinear. So we would have looked at collinear quite recently when we did the area of a triangle. Remember, collinear means lie on the same line. So here's my point of contact. There's my center 1. There's my center 2. Similarly here, center of the big circle, center of the small circle, center of the point of contact. So we talk about these circles as touching externally. So if you look at the diagram, hopefully that makes sense why that's called externally, because they're touching outside. And then this one is called touching internally. And we'll do a lot more with this. And actually that's the basis for quite a lot of our exam questions. So this idea that the circles touch externally and internally, and we'll do a little bit more about that when we come to that section. So the last theorem is theorem 21, and this is also a really, really important little theorem that comes up in quite a number of circle questions, and we utilize it. And it basically says the perpendicular from the center of a circle to a chord bisects the chord. So remember that bisects means to cut in two equal pieces. And you can see here that they've done our double lines to show that the perpendicular from the center, so here's my center point, and the line comes through the chord and it is perpendicular. It will bisect the chord. And then the second part is this: the perpendicular bisector of a chord must pass through the center of the circle. So if I know that line cuts the chord, then I also know that line must go through the center. And if it continues to the other side of the circle, it will be a diameter. So that is ready to be stuck into your copies. So let's jump straight into an example. Find the equation of the common chord / tangent of two circles. Now, the reason we've said chord or tangent, excuse me, there will be two scenarios. The first scenario is where the two circles overlap. Where two circles overlap, there will be a chord. So this is what it looks like when I have two overlapping circles. So they'll have this common chord AB. And just to remind you, a chord is a line which goes from one edge of the circle to the other. The diameter is actually a special chord which goes through the center. If the circles touch, so this scenario here, they won't have a chord in common, they'll have a tangent in common. Now, the good thing is the method will be exactly the same for getting the equation of a chord or a tangent. So for us, it doesn't actually, we don't need to know if they overlap or if they touch for this particular question. If we're just finding the equation of the common chord or the common tangent, the methods are exactly the same. So the equation says, the example says, find the equation of the common chord. So they've told us we're looking for a chord of the two circles x squared plus y squared minus 6x plus 2y plus 4 equals 0, and x squared plus y squared plus 2x minus 4y minus 6 equals 0. So we actually have this scenario here. So I've just changed the picture back, but again, it doesn't really matter. The methods are exactly the same. So there's a few different ways where there's a few different ways how people approach this, but I'm going to work with this like I'm working with elimination. So our elimination method of simultaneous equations, and that's where we put one above the other and we work with it. Now, when we deal with elimination, up to now it's always been linear. So linear where we have two equations, or linear three equations, so two variables or three variables. Here we do have two variables, but they're both non-linear. So what we're actually going to do is we are going to eliminate, but we're not going to eliminate the x's or the y's. We wouldn't be able to. What we're going to do is we're actually going to eliminate the squared terms. So what I'm going to do is I'm going to change my signs here. So that becomes minus, 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 plus, plus, and my 0 doesn't need to change. And I eliminate my x squareds and I eliminate my y squareds. And what I get is minus 8x plus 6y plus 10 equals 0. And that is actually the equation of the common chord. Now, I wouldn't leave it in this format for a few different reasons. The first being that there's a minus in the front, and also that it can be simplified. So if we want to simplify this down, you can see hopefully that there is a 2 that's common. So I'm going to divide across by minus 2, which will give me 4x plus 3y, minus 3y, minus 5 equals 0. And that is the equation of the common chord. So it's a nice little straightforward question. There's nothing too difficult on it. Sometimes people show it algebraically with one equation, subtract the other equation like on one specific line. I think because we're used to this elimination method, I prefer this. I think it's less likely that it will go wrong with your signs. But any other method is absolutely fine as long as you are eliminating the x squareds and the y squareds. Just be careful for maybe circles where the coefficient of the x squared and y squared aren't necessarily 1. You might have to do a little bit of work with it, but we tend to see them quite straightforward like this. So example 2, find a point of intersection between two circles. So find the equation of the common chord of the circles, this and this, and hence find the coordinates of the point of intersection. Okay, so the first part's very straightforward. We've just done that. So let's do that again. X squared plus y squared minus 3x plus 5y minus 4 equals 0. X squared plus y squared minus x plus 4y minus 7 equals 0. So again, I'm just going to change my signs. It's the easiest way to work with it. When I change my signs, I generally use a different color because if I want to go back and check my question, I won't have written over it in the same color. I'm able to see really quickly, have I changed my signs? I'm able to check my work quite quickly. Plus y plus 3 equals 0. Now again, I like to start with a positive just because the reason I actually will always try start off any equation with positive is because if you have a negative at the front, it's very easy to lose that negative. And when the negative is between two numbers, we tend not to lose it as easily as we lose it at the start, especially if you're rushing, if you're working across a few lines and the minus turns into one of your lines on your copy, anything like that. So it's not wrong if you don't, but it's a trick that I would always do to make sure that we don't lose that minus. So that's the first part done. And just for my own benefit, I'm going to write underneath what I've got. So I have the equation of the common chord. Now, very straightforward little question, but then they've added on the hence. Hence find the coordinates of the points of intersection of the two circles. Now this is where it will differ slightly between the common chord and the common tangent. The chord will have 2 points of intersection, while the tangent will only have 1. So it'll only be your answer will be slightly different. So just to bring back up the picture, we have this scenario here. We have two circles and they touch here and here. Now when we do elimination, notice that our answer gives us an equation. It leaves us with an x and a y. It won't be possible to eliminate the y's and the y squared, so like all the y terms, because usually the numbers won't be in our favor. Now if they are, it's a coincidence, but we will have to work with this particular method. A lot of students go into the exam and they will try to do elimination to get the points of intersection, but that won't give you the points of intersection, that gives you the equation of the chord. However, it's a very, very important first step to get the points of intersection, because now what we're going to do, we're going to take the equation of the chord and the equation of one circle. So we're going to find points of intersection between the chord and one of the circles. And it shouldn't matter which circle at all between the chord and one of the circles. It shouldn't matter at all. Both answers should be exactly the same. So I'm just going to clear the page to start that process, but just as long as you're clear in your head what we're going to do.
So with this linear, I'm going to take the first circle. I'm going to call this equation 2 just so we can keep track of everything. So that is x squared plus y squared minus 3x plus 5y minus 4 equals 0. Now this is my non-linear. So this is exactly the same process as we'd have if this question was asked in like a section A of paper 1. So where we're asked to find the point of intersections of a linear and non-linear. It's the exact same method. What I'm going to do is I'm going to take my linear, I'm going to isolate a term. Now it can be either the x or the y, it doesn't matter, but choose one that's easiest. So I think, excuse me, it would be much easier for us to isolate the y because the y has only a coefficient of 1. So when we rearrange that, now what I'm going to do is I'm going to add a y to both sides, and then I'll get y is equal to 2x minus 3. Now it may look like 2x minus 3 equals y, but then I'm just going to rewrite that or flip it. So that's my linear. Now what I'm going to do now, I've isolated y, I'm going to substitute that value of y, or rather that y in terms of x, I'm going to sub that into my non-linear. So the purpose of this is to remove one of the variables. We can only ever solve for one variable with one equation. So because we have two variables, what we want to do is effectively eliminate one of them. We can use elimination method when we have two linears. Because we have linear and non-linear, we use this method called substitution. So this becomes, so my equation 2, just always labeling to keep track of everything, x squared plus, instead of y squared, I have 2x minus 3 squared minus 3x plus 5. Instead of y, I put in 2x minus 3 minus 4 equals 0. Now I'm going to expand any of the brackets and then tidy up. So this becomes x squared plus, using the shortcut for squaring, 4x squared minus 12x plus 9 minus 3x plus 10x minus 15 minus 4 equals 0. Now this is quite long, so do be careful and use highlighters, or like here I can't really, well, highlighter is a bit more of a pain to use here, so I'm going to use kind of shapes to help me add any like terms. And then I have a plus 9, a minus 15 and a minus 4. What we'll get now is a quadratic. So my quadratic is 5x squared. I have minus 12x, and actually if there's a lot going on you can tick them off as you use them. So we have minus 12x minus 3x plus 10x. So that's minus 15x plus 10x, so minus 5x. So there's all the x terms used. And then we have minus 15 minus 4, that's minus 19, plus 9, so that's a minus 10 equals 0. The quadratic that we have here, it can be simplified by dividing across by 5. That will make it a little bit easier to work with. So instead we get x squared minus, you can again write 1 if you want, but just minus x minus 2 equals 0. And if we want to go and factorize that, we can use the shortcut for guide number or trial and error, whatever way you're working. So minus 2 in one bracket, plus 1 in the other, and that gives us a final answer for x as 2, or x equals minus 1. Now, if we go back to the question, we've been asked for the coordinates of the points of intersection. So it's not enough to just give the x values. We need to go back in and find the y values. To find the y coordinate of the points of intersection, it will always be easier to go back to not the original linear, but the linear where we isolated the term. And the reason for that is we've already done the hard work. So I'm going to use the y equals 2x minus 3. So y equals 2x minus 3. I then sub in what I already know for x, that's 2 times 2 minus 3, so I get y equals 1. So very, very straightforward, no need to do any kind of moving things across the equals, adding, subtracting, dividing, because I've already done that hard work when we've isolated that y. So my point here is 2, 1. Then working around x is equal to -1, y is equal to 2x minus 3 again. So y is equal to 2 times -1 minus 3. So y is equal to -2 minus 3, that is -5. So we get a final answer of -1 minus 5. And there are our points of intersection of the two circles. Now I did use the first circle when I worked through this process, but you should get exactly the same answer if you work through with the second circle.
Okay, so example 3, investigate if circles touch internally or externally. So both questions can be asked. So this first example will be about touching externally. So show that these two circles, S1 and S2, touch externally. So here's a diagram of what two circles that touch externally look like. We've already said with regards theorem 20, the corollary of it, where the center of the first circle, the center of the second circle, and the point of intersection, they're all collinear. They lie in the same line. So looking at this picture here, what method or what little piece of information we use to figure out whether circles touch internally or externally? It's the distance between the centers. So if you look here, the distance between the centers is equal to radius 1 plus radius 2. Okay, so the distance between the centers is radius 1 plus radius 2. So if that's true, they must touch externally. So what we're going to do, we're going to take each circle and we're going to go to page 19 in our log tables, and we're going to take the circle formula. So x squared psi squared plus 2gx plus 2fy plus c equals 0. And from there you should be able to pull out 2g equals -6, so g equals -3, 2f equals -4, so f is -2, and c is 11. And then from the log tables as well, they tell us that the center is -g minus f. So my center for this circle is -g, which is 3, and -f, which is 2. And they also tell us the radius is equal to square root of g squared plus f squared minus c, which for us it's the square root of -3 squared plus -2 squared minus 11. So if -3 squared is 9, plus -2 squared is 4. 9 and 4 is 13. Minus 11 is square root of 2, and that is our radius. Show by all these pieces. So the square root of 2 is our radius. So that's my first circle. So that's all S1. So we're going to do the exact same thing for S2. So I've just cleared a bit of space and I've given just what we've worked out here. So the details for S1 are there, and we're going to do exactly the same thing when we're dealing with S2. So S2 is x squared plus y squared plus 4x plus 6y minus 19 equals 0. And again, page 19, I have x squared plus y squared plus 2gx 2fy plus c equals 0. And we have 2g equals 4, so g equals 2. 2f equals 6, so f equals 3. And c equals -19. So again, we have from page 19, minus g minus f is the center. So that's -2 minus 3. And my radius. So my radius is given as square root of g squared plus f squared minus c. I'm working that out. Square root of 2 squared plus 3 squared minus 19. And that gives me root 32, or 4 root 2 when it's simplified. So now that we've got the details of both circles, we have the center of both circles and we know the length of the radius for both circles, we're now going to get the distance between the center points and compare them to the sum, so when we add together the two radii. Okay, so now, again, I've just written all my details over here on the left. So now what I want is I want to get the distance between the centers. So my two center points are 3, 2 and minus 2, minus 3. So I'm going to label these x1, y1, x2, y2. And on page 18, I'm going to take my distance formula, which is x2 minus x1 squared plus y2 minus y1 squared. And I'm going to sub in. So I have the square root of minus 2 minus 3 squared plus minus 3 minus 2 squared minus 5 squared, so I get 25 plus 25, which is the square root of 50. And simplifying that on our calculators, we get 5 root 2. So now I want to compare it. So d is equal to radius 1 plus radius 2. That's been my formula since kind of the start, based on the picture there on the left. So d being the distance between its centers, or 1 being the first radius, or 2 being the second radius. So the distance between their centers is 5 root 2. Radius 1 is root 2. Radius 2 is plus 4 root 2. 5 root 2 equals 5 root 2. So, since that is true, we can say the circles touch externally. So therefore, circles touch externally. So example 4, again, we're dealing with the same kind of question, investigate if circles touch internally or externally. But this question says, show that these circles touch internally. So what exactly do we mean by touching internally? So here's my diagram. I have two circles and one is within the other ones. This is what we mean by internally. So the smaller one is inside the bigger one. So one will have to be smaller than the other for this to work. If they were the same size, then they would literally be the same circle because they're in the same place. So they'd have the same equation and the question wouldn't make sense. This is the one that students tend to have a little bit of trouble with, because what we're basically saying is the distance between the centers, which is this piece here, that's actually equal to the difference in their radii. So actually that is equal to R1 minus R2, where R1 is the bigger radius. So it's very similar to our last question, but it's this piece here that tends to make this one a little bit tougher for students. Students find it harder to remember. So we're going to do exactly like we had done in the last question. We take our equations and we set up the equation using page 19 our log table. So x squared plus y squared plus 2gx plus 2fy plus c equals 0. 2g equals 4, so g equals 2. 2f equals minus 6, so f equals minus 3. And c equals 12. So then the two things we can talk about, again from page 19, minus g minus f is my center point. So I get minus 2, 3. And my radius is given as square root of g squared plus f squared minus c, square root of 2 squared plus minus 3 squared minus 12, which equals, and that's actually square root of 4 plus 9, 13 minus 12, square root of 1, which is 1. So now let's work on the second circle, which is x squared plus y squared minus 12x plus 6y minus 76 equals 0. Again, going to page 19, x squared plus y squared minus 2gx, plus 2gx plus 2fy plus c equals 0. I have 2g equals minus 12, g equals minus 6. Here I have 2f equals 6, so f equals 3, and c is equal to minus 76. Again, going to page 19, so my center is minus g minus f. So that is 6 minus 3. My radius is then square root of g squared plus f squared minus c, square root of minus 6 squared plus 3 squared minus 76. What's your signs on there? On that minus c. If it is negative, you're subtracting the negative, so it will become positive. 36 plus 9 plus 76, so 45, 121. So my answer is 11. Okay, so now we have all details for our circle. We're going to go and try work out the distance between its centers, so then we can compare it to the two radii. So the method is pretty much the same as what we had for example 3. It's the very final step will be slightly different. So we're going to find the distance between the centers. So we get minus 2, 3, and we have 6 minus 3. We're going to label x1, y1, x2, y2. Our formula is x2 minus x1 squared plus y2 minus y1 squared. Subbing into our formula, we have 6 minus minus 2, so plus 2 squared, plus y, which is minus 3 squared. So we have 6. So 64 plus 6 squared, 6 is equal to square root of 100, which is equal to 10. So now we're going to go back to this. Is the difference between the two radii, is that equal to the distance between the centers? If so, then yes, they do touch internally. So my distance is 10 is equal to R2, which is 11 minus 1. This is true, therefore circles touch internally. So a good idea for questions like this is just have a little sketch done out. What does it mean about touching internally? What does it mean about touching externally? So now that we've discussed circles that touch internally and externally, I'm going to show you a second method where we can find the point of intersection of two circles that touch externally. So the circles C1 and C2 touch externally as shown, and the equation of circle 1 is given here, and the equation of circle 2 is given here. It's asking us to find the point of intersection of these two circles. So our previous method to find this point here, this point of intersection, was to find the common tangent, and that was simply subtracting the equations of the circle, so using elimination to get that common tangent, and then doing simultaneous equations with linear and nonlinear to find the point of intersection for between the circle, well, one of the circles, and the common tangent. Now that method is absolutely perfect and can be used here. However, there is a little bit of a shorter method that you may prefer to use. So the first thing we're going to do is we're going to work out the center and the radius of each of the circles. So taking our equation as per page 19, so x squared plus y squared plus 2gx plus 2fy plus c, we can take out that the center, which is minus g minus f, is minus 3 minus 2. And our radius, we can work out using again the formula on page 19. It's the square root of 3 squared plus 2 squared minus 9, and that works out as 2. So doing the exact same thing for circle 2, we get 1, 1, so minus g minus f. And our radius for circle 2 is the square root of minus 1 squared plus minus 1 squared minus 7. And that gives us square root of 9, which is 3. So what we've just discovered is this center here is 1, 1. This length here is 3. This center here is minus 3, 2. And this center is 2. So what we're actually able to do here is to use our formula, which is on the bottom of page 19, which is a point dividing a line in the ratio A is to B. So using that division of a line formula, we can find that blue dot, because if you look at that point of intersection, that's dividing the line that sits between minus 2 and 1, 1 in the ratio 2 is to 3. So if I take the point minus 3 minus 2 and 1, 1 as x1, y1, x1, y1, x2, y2, and I take my ratio as 2 is to 3, and again on my log tables that's the ratio A is to B. It's really important that whatever point you start with, so we started here, then the first piece is how long that should be. So 2 is to 3. So we start from that point, 2 is to 3, and we end at 1, 1. So the formula for this is bx1 plus ax2 all over b plus a, comma by1 plus ay2 all over b plus a. And working that out, we get 3 times minus 3 plus 2 times 1 all over 3 plus 2. Again, 3 times minus 2 plus 2 times 1, 3 plus 2. I'm working that through. Minus 9 plus 2 over 5 minus 6 plus 2 over 5, and that gives us minus 7 over 5 and minus 4 over 5, which is the point where those circles intersect. So there's also a shorter way where we can find a point of intersection of two circles that touch internally. So again, the same method could have been used as before, where we go and we find the common tangent. We then find the point of intersection between the common tangent and one of the circles, and that method will work absolutely fine, but this is just a little bit shorter. So the two circles S and C touch internally at B as shown. The equation of the circle S is given as this, and the equation of the circle C is given as this. Find the point of intersection of the two circles. So we're going to work in a similar way as we did the last time, but because they touch internally, our workings are going to be slightly different. So the first thing I'm going to do, just like before, is I'm going to pull out the center and the radius. So circle S. Now, this is not the usual form that we see it in. We're working instead with the middle of page 19 rather than the bottom of page 19. So we're looking at given center HK and radius R. So the center here is 1 minus 6, and the radius is equal to the square root of 360. That simplifies to 6 root 10. And for circle C, I have 5, 6, and the radius there is square root of 40. That's 2 root 10. Okay, so we have that information, and just to put that on our diagrams, this is S, this is 1 minus 6. That center K there is 5, 6. And we have this line here, and we're basically trying to find B. So I'm just going to sketch it down here just so we have a little bit more space to see it. So here's the point 1 minus 6. Up here is the point K, which is 5, 6. And this is the point B that we're trying to find. Now, if we think in terms of length, this we've just worked out as 2 root 10. Now we've worked out the whole line is 6 root 10, so this part here must be 4 root 10. So we actually could work this through as a ratio as 4 root 10 is to 2 root 10. Now, ratios work like fractions, we can cancel it down, so this actually gives us the ratio 2 is to 1. So that line there is actually in the ratio 2 is to 1. So just like our previous example, we're going to try and use the point dividing a line in a given ratio formula, and we're going to use the point 1 minus 6. And the end point is B, which we don't know. So we're just going to call that xy for the moment. And it's going to be in the ratio 2 is to 1. So this is my x1, y1, x2, y2, and this is a is to b. Now the difference is when I do this formula, so we get bx1 plus ax2 all over a plus b, by1 plus ay2, sorry, actually it's b plus a, the log tables, it won't make difference, but let's just change it so it looks like our log tables. So when we fill into this, we have 1 times 1 plus 2 times x all over 1 plus 2. And here we have 1 times minus 6 plus 2 times y all over 1 plus 2. And we know that this should give us the point in the middle, which is 5, 6. So this formula, along with the midpoint, is one of the few we can use to find out an individual x and y because of the way that it's structured. So we're going to work these two pieces through and see what we can work out for x and y. So let's work with the x coordinate first. So we get 1 plus 2x over 3, and that should equal 5. Working that through, I get 1 plus 2x, multiply both sides by 3, I get 15. 2x is 15 minus 1, so 14, so the x is 7. Working through the y coordinate, we get minus 6 plus 2y over 3 equals 6. Again, multiply both sides by 3 to get rid of the fraction. 2y equals 18. 2y equals 18 plus 3, which is 24, so y is equal to 12. So my point is 7, 12.